All right, my name is Christopher Meiklejohn. I'm going to talk about scaling the distributed actor runtime with Partisan. So distributed actors have been used on a lot of highly scalable, highly concurrent applications. They have tremendous industry success. As I discovered yesterday during the poster session, not many people know that these programming languages even exist. So hopefully this talk will raise some awareness about that. This is really not my conference, is it? I hope that stays in the video just because. Is it? Yeah? Okay. All right. And so distributed actors, they're really successful. And you probably know some of the applications that they've been used on. Fortnite is a pretty popular application. Gears of War 4, Halo, these are popular games. League of Legends, you may have heard of. And WhatsApp, I'm sure a lot of you are probably using at this very moment, especially when my mic fell off my lapel. And so each of these actor systems uses one of the three major industrial strength. Each of these applications uses one of the three major industrial strength actor systems. So Fortnite, for instance, uses Akka cluster for the Scala programming language. Gears of War 4 uses Microsoft Orleans, as does Halo. And League of Legends and WhatsApp use the Erlang programming language. Now, part of the success, part of the reason that distributed actor systems are so widely adopted is because of this programming model. It's very simple. So first I'm going to explain this function definition here. So this is defining a function called call. It takes three arguments, a destination process ID, a message, and a timeout period. We use this bang syntax here, destination bang message, to send a message to a destination process. And we use this receive primitive to wait for a response. And this will perform pattern matching. And finally, with this after clause and this timeout, I'll wait a particular amount of time for a message, then I'll time out and return an error to the user. So once I define functions, then I use this spawn primitive to instantiate actors in the system. So here I say, I'd like to create an actor. Here's the function I'd like to call. And the actor will run that function to completion and then terminate. So this is a nice programming model, and it's really, really nice for building distributed systems because you don't see networks, you don't see sockets, you don't see serialization, you don't see deserialization, you don't see any of the stuff that we usually don't like writing when we're writing distributed code. And all of these three actor systems, whether it's Akka, Orleans, or Erlang, all of them have the same programming model effectively, but slightly different because they have different host languages. So in this talk, we're going to look at how we can improve distributed actor systems considering their two limitations. The two limitations are scalability and latency. Now, in terms of scalability, we're going to increase scalability by growing clusters to larger clusters of nodes. And in terms of latency, what we're going to attempt to do is use available bandwidth to perform scheduling in parallel to reduce latency and increase overall system throughput. Now, we're going to achieve this with minimal modifications to the programming model. We're going to do this at the library level, which is really nice. It's extensible. We don't have to ship a custom runtime. We don't have to ship a patch set for a custom runtime. We don't have to make our own runtime. So let's dive into the limitations. So the first limitation is around scalability. Here, I have a cluster of 3 nodes. Each is running 2 actors. And these nodes are connected in a full mesh topology using TCP. And what this means is when I add a 4th node and I spawn 2 actors, instantiate 2 actors on this node, I also have to connect this to all the other machines in the cluster. Now, these assumptions around having to connect all of the nodes together, because these systems have to transmit metadata information, they have to send heartbeat messages to keep the system operating. Because of this, scalability is limited. We end up exhausting communication and spending a lot of time in serialization for messages that are just for keeping the system running. Not even considering the requests or responses. And this is evidenced by kind of these 2 data points that we have here. Our work focuses on Erlang, so my 2 data points here are on Erlang. But one is that the only people who have been able to run distributed Erlang at 200 nodes is Ericsson, the people who made the language. And similarly, the database that I used to work on before I quit my job to do my PhD, REAC, is a Dynamo-inspired Cassandra-like database. This database only used to scale to 60 nodes. So that's not good for a distributed data management platform, surely. Now, the second limitation is around latency. If I consider a 2-cluster node, 2-node cluster, and I connect these 2 nodes, and then I spawn like thousands of actors on node 1 and thousands of actors on node 2. what I need to do is use that single TCP connection to multiplex all my communication for any actor to any other actor on either side of the cluster on either node. And this results, in queuing delay. There's head-of-line blocking that happens when you have messages sending at different rates and different sizes. There's network congestion issues where you're running this in geo-distributed scenarios or you're running it with large objects. And finally, everybody's contending for access to this socket. And that doesn't work when I'm mapping like 100,000 actors into one TCP connection. So how do we solve this? So the work that we're going to talk about today is called Partisan. It's a library that I've been working on for at least 2, maybe more years now. It's a system that's designed to remove assumptions around current implementations that are made by runtimes, these full mesh assumptions, these single TCP assumptions. And it's provided in user space as a library so that it can be extensible, it can, you can use a debugger, all of this nice stuff, and it can be leveraged immediately. You can use it in applications today. And so the key contributions of Partisan are, first, allowing the application developer to specify the communication strategy, the communication overlay that's used at runtime without changing application code. And the second is enabling parallel transmission on the network. So let's look at the first contribution. So the first thing is around selecting the overlay. So like I said before, we connect all these things in this full mesh. Everybody communicates with everybody. And the insight here is, if we want to change the communication strategy, we shouldn't let that be evident in the programming model. We don't want that to come up and expose itself in the programming model. We want to keep the programming model the same. We want to preserve the existing semantics. And so here, just to reiterate the point, we really want to look at this as not changing anything because we have a model that's really successful that people are building these great applications in. So in Partisan today, we have this full mesh topology. This is the default topology. It's the simplest to reason about. It operates really well when you have smaller clusters. And what happens is I connect all my nodes completely, and then I use direct messaging to do point-to-point messaging. So my API is point-to-point messaging. We also provide a second topology called client-server. This is a familiar hub-and-spoke kind of model, right? Servers talk to servers, clients talk to servers. And what this means is that clients do not directly communicate with other clients. And so the programming model, to remain point-to-point, we have to have servers route messages on clients' behalves so that clients can still message one another. Similarly, the peer-to-peer topology scales to massive clusters, 10,000 nodes, 20,000 nodes. And because of this, every node needs to only connect to a portion of the network, right? And this means that you might not even have a server to route messages on behalf. So we have to do this transitive routing. We have to have messages handed off between peers to get to the final destination. Now, the second set of optimizations we'll look at is around application enabling parallelism on the network. We're going to break this down into 2 techniques. So the first technique is called name channels. And the way name channels work is under the assumption that we have this cluster of nodes with different actors sending different types of messages. So some are request responses, and some are maintenance traffic for the cluster maintenance itself, right? And so in the React distributed database, we have to gossip a ring around. We have to gossip metadata. We have to send failure detection information. And what we want to do is we want to say, get all that stuff out of the request path, unless it's absolutely necessary, put this onto a different channel, and let's pipeline these requests on this single path. Now, we have to, in Erlang, we have to annotate all the call sites with message types. This is unfortunate. But this is because Erlang really has no types. You don't know what anything is. Everything is basically just a term or a tuple of terms. And so we can't do this at runtime automatically. But in a system like Scala, where you have a really rich type system, in a system, in a programming language like C#, we can do runtime reflection. And by doing runtime reflection, we can do this automatically. And so key here, take the types and partition traffic on multiple connections based on types. Now, a special case of that technique, a special case of named channels, we can try to keep actors working on one connection. And we can do this by affinitizing the traffic from multiple actors onto connections based on their sender identifier and based on their recipient identifier. Or we can use a logical identity if actors happen to take on different roles over time, which is common in actor systems. And so what this does is it lets us kind of take advantage of kind of pipelining operations where we have these request response patterns to a group of actors, such as in a distributed database. So let's see how all of this stuff runs. Let's run some experiments. I'm going to talk about 3 sets of experiments today. The first experiment I want to talk about is a scenario that came from an industrial partnership we had with Rovio Entertainment, who makes Angry Birds. This is an advertisement counter. I'll explain it in a moment. The second set of experiments we'll look at is point-to-point experiments for looking at round-trip messaging, kind of round-trip performance of messaging. So these will be a set of micro-benchmarks to examine the impact of our techniques on latency and how we can reduce latency. And then finally, the last set of benchmarks are based on the distributed programming framework React Core, which is an implementation of the Amazon Dynamo model in Erlang. This is the actual framework that's used in the production React database that's deployed at the NHS and all these other places. And we build two applications on top of this. So we build a simple echo service, so we're bound only by the speed of the network. And then we build a little mini key value store, distributed database, writes to 3 nodes, waits for a majority, kind of like Cassandra operates. So let's talk about the Rovio example. So the Rovio example is an advertisement counter. So if you consider, if you're playing Angry Birds, some of you might be playing Angry Birds right now, for all I know. If you play Angry Birds, sometimes you'll see an ad. And what we want to do is we want to aggregate the ad counts. We want to aggregate the number of times ads have been displayed to all of the users. And we want to turn the ad off when we've shown a minimal number, like a lower bound, so at least 5,000 impressions. And what we're going to do is we're going to replicate this counter on everybody's device, and we're going to periodically synchronize this counter. And then we have this threshold trigger when the ad is shown X times. So here's our 3-node cluster. We have an actor on each node. We increment the local counter, and then we propagate that counter to the other nodes who merge it in. And so this keeps this counter moving forward as it's incremented locally and sent to all the other replicas in the system. Now, we run these experiments on EC2. They're not simulated. We didn't use PeerSim. And we're going to look at 2 of our topologies, client-server and peer-to-peer. We're going to use a fixed number of increment operations. And this means that the amount of state that we generate for every experiment is the same, but we're going to see the effect on redundancy in the overlays and different communication paths on the amount of data we transfer. So here we have a graph. On the y-axis, we're plotting data transmission to complete the experiment in log scale. On the x-axis, we have the cluster size from 32 up to 1024. The black bar represents the client-server topology, and the gray bar represents the peer-to-peer topology. Now, what we see here first is the data transmission serves as a proxy for redundancy. So in the client-server one, all the messages are sent to each destination once. They're routed through the server. So that's kind of our lower bound, the minimal kind of data we have to transfer. But with the peer-to-peer topology, we see because there's redundant links, people might get the same message down multiple links multiple times. And so what we observe here is that at these lower cluster sizes, these less redundant overlays that are better for smaller clusters, they're more efficient on the wire. They send less data. But as we observe here, the trend with peer-to-peer is that the peer-to-peer keeps scaling. And we had to stop our experiments here because I had spent quite a bit of the European Union's money where I was doing this work. So we had to stop at 1024, but we could have kept going. And so at this 256, when we get to 512, we see the server instance runs out of memory to start addressing the clients. It actually, message queues in Erlang are unbounded, so when you send somebody a lot of messages, they run out of memory. And then the killer kills the instance. So kind of the takeaway here is peer-to-peer. We got nice scaling properties, but it's a little bit more expensive when we don't need it. And then the client server is really efficient on the lower end. So latency benchmarks, we'll get right into them. So with the latency benchmarks, what we're going to do is look at round-trip time for sending individual messages on the wire. We're going to simulate 20 milliseconds of round-trip time latency to simulate intra-DC in the same region for Amazon. We have other experiments, but I found this one interesting to show. So this is the one I picked. We're going to use a 512 kilobyte payload size. And we're going to graph in red, distributed Erlang. In green, Partisan with only a single TCP connection. This will serve to show how much penalty we pay by being in user space. And then in teal, we're going to see Partisan with some of our optimizations and 16 connections. And then in purple, we're going to see the total optimal config. So again, just to reiterate, the things you want to be paying attention to are to red, distributed Erlang, that's the baseline. Partisan, that's the purple. All right, so the first thing we see when we see this red to green is that the Partisan performance is competitive even with the user space implementation. So regardless of not being in the kernel, not being written in C, we remain competitive. We see that with the green bar, we start paying when we have a single connection, we're paying penalties for context switching in user space. But as soon as we affinitize connections and take advantage of our optimizations, we can get a 13.5x improvement for 128 actors. We have details in the paper why we chose 16 connections. Now in throughput, the throughput experiments are going to use a key value store and an echo service where we will issue requests to a normal distribution over 10,000 nodes. We'll look at how many operations we're able to perform per second. And then in our key value example, what we'll do is a fan-out, fan-in Cassandra-like pattern. And so here, on the x-axis, we're varying the number of actors. We got throughput per second on the y. In the red, we're going to have 1 kilobyte payloads. Green is 512, and the bottom is 8 meg. If we focus in on 128 actors, we see that we're roughly the same when it comes to, does that count the mic part? We see that we're roughly the same performance when there's red and green, when we have 1 kilobyte and 512 kilobytes. And then finally, we get to here, with 8 megabytes, we get a 2.84x improvement. All right, so I'm basically out of time, but I want to show this last graph, because this is kind of the most important graph here. And so this is the key value store. This is the fan-in, fan-out fan-in, fan-out pattern. So it's like Cassandra. Now, what we observe here, if we focus in on 128, is that we have roughly the same performance when we're dealing with 1 kilobyte objects. Now, when the object size starts increasing here, we get a 1.5x when we move to 512K. And then when we move to 8 meg, we have 104 operations per second with the partisan performance. But distributed Erlang's throughput completely collapses, and we only complete a single experiment for the duration of the execution. Now, this is an interesting result because React operators, anecdotally, were told in the documentation, it's still online, you can go look at it, to don't store objects in this database that are greater than 1 meg because you'll kill the throughput of the system. You'll actually crash the performance because the network carrier will collapse. All right, so to conclude, distributed actor systems here have typically been limited by implementation assumptions. They have not been limited by the programming model. As we saw, it's just sending messages. Most of these design decisions were made in the early 90s when we were deploying to single data centers. And we believe that our work design fills a need for improved large-scale actor runtimes. Now, we believe this to be true because previously React implemented their own transport for large objects and geo-distribution. They're considering Partisan as a replacement. In React CS, this was software that was developed to store large objects under the S3 API. They did 1 megabyte chunking, so an engineer spent a long time building 1 megabyte chunking because of a problem in the runtime. And then finally, there's 2 new applications I'd like to mention that have been built on Partisan. BarrelDB uses our parallelism optimizations and our overlay for providing a large-scale peer-to-peer replicated database. This is built by former developers of CouchDB. And then Bondi is a RPC transport layer for hundreds of microservices that has been running in production for 18 months using Partisan. So to conclude, we believe that our work enables new types of applications built using distributed actors. And I think we've shown evidence that you can do large objects and you can do geo-distributed applications. And we also believe that we've paved the way to start using actors where they haven't been seen before. Maybe client-server applications, maybe mobile devices, who knows? And so thank you for coming to my talk. If it was your first time, thanks for it. And if it was your second, special thanks for it.
Hi. Do we get to ask questions?
Yes.
Yeah, OK.
Please.
Well, I was wondering. So I'm Eric Eide from the University of Utah. This is, I think, really great work and very interesting work. So it seems that Partisan is like a win in every dimension. So it should just go into Erlang tomorrow. So why won't it go into Erlang tomorrow?
So that's a really great question. So there are a couple things going on there. So first, since we didn't have runtime support, we don't support sending closures. Now, this is an interesting thing because I don't believe there's anything stopping us from doing it, but we're also a little dogmatic about it because we think it's really bad to send the reference to the number of a closure in some source file that the remote mode might not even have loaded or have a different version loaded. So functions are a problem. Another one is around, there's references. Actually, no, references are fine. There was one more around some of the failure detector behavior. So the failure detector basically counts, it sends heartbeat messages and it waits for like a heartbeat interval to elapse, like, oh, I missed so many heartbeats. I'll consider all of the remote actors dead. And so this failure detector is used to build links and monitors. And so people like doing this cross-node. And so it's really difficult to do this efficiently with the peer-to-peer overlay, because it kind of assumes that if I need to know that some actor on that remote node is alive, then I need to maintain a connection to it so I can tell that, right? And so this existing semantics of Erlang would not be able to be mapped into this immediately until we had a good solution. One solution is to transitively find out if somebody is alive, but then that makes the failure detection interval really long. So maybe the failure detector is less useful there. So these have been like the big things. These kind of two features that we don't really know how to handle just yet. So yeah, so that's kind of the blocking stuff with OTP and Erlang.
Thank you.
Yep, or the beam rather.
So one quick question.
I just had a quick question about actor migration. It seems like actor migration is made more complicated with Partisan because all of a sudden you don't have this full mesh topology.
So which actor migration?
If I wanted to migrate an actor from one host to another host.
Yeah. So I mean, in Orleans, so the Orleans solution there is, to kind of coordinate via cloud storage, right? So I say like I'm going to terminate my actor on node A. And I'll store the state in durable cloud storage that's addressable by anybody, and then I can kind of rehydrate that actor on another node based on that cloud storage. So I think that's the right model, and I don't think that anything about our model would prohibit that model from working. And I think that's a proven model that's been used on Halo and all of this stuff for actually doing this stuff at scale. So I think that's the right model for migration.
Thank you, Christopher.
Thanks.